So we try using this bit pattern here just for some sort of recognizable value. So let's just say that this is recognizable bit pattern. And the important thing is that the way it's written, it's pretty simple idea. We start pushing things on the stack, essentially start using this stack memory segment. But if the way it's written right now, if we attempt to return, remember the last push instruction is making register ESP pointing to this value on the stack. So if this is the value on top of the stack, this is where ESP will be pointing to the last value pushed on the stack. So if we attempt to return, it will be using this return address. And of course, this will very likely result in some sort of memory access violation, trying to execute instructions in area where we don't even have permission to execute. So this is bad. So what we need to do is that we need to say pop, for instance, again, we can pop the same register EAX, and then we can say pop EBX as an example, right? We can pop another register here. So the comment here would be that we restore EAX, because it was all this time here we could write many more instructions and things in our code, but right here we still had a value preserved on the stack. Oh, and I'm sorry, I should probably say pop EBX, so this would restore the last saved value, right? So this will actually restore value 5 into EBX, right? So register EBX will be set equal 5 as a result of this. And then we need to restore register. If we want to restore register EX, we have to do it as a last step in this sequence of instructions, because remember that what is going to be happening here is that, again, in this diagram that we have, this will be the return address on the stack, which we get from the call instruction. And this is where ESP originally is pointing to, but then we say push EAX, so we save EAX on the stack because we decided to do that, preserve value of the register. Then we say 5, okay, and then so this is the situation where we're having right here. So when we say pop EBX, what will be happening is that at this stage ESP is pointing to the top of the stack, and that is the last value that was pushed into the stack. So pop EBX, this first pop instruction, will copy the value of 5 into EBX, right? So it's just basically it will be retrieved right here, and then pop also adds 4 bytes because EBX is 4 byte size. It will adjust the stack pointer to the next value, so this becomes new top of the stack. And now the next step is pop EAX, and of course will be indeed restoring the value of EAX. So all this time, right, from here to here, we kept value of EAX preserved on the stack, and push 5 has a matching pop instruction. So this is how your push and pop instructions are supposed to be organized. So they're basically, their sequence is a mirror image, not the same sequence, but the reversed sequence. So the last thing is getting popped first. Remember this principle LIFO. Last in, first out. This is how we're supposed to be using the stack. So that's pretty much the only careful thing that you have to remember, because like I did this originally, just casually copying and pasting this and changing the instructions to pop, right, would be a really bad idea, because you really have to rearrange the order of the instructions. Also, this is not good because, of course, you cannot pop into an immediate value. So this instruction would not does not exist. You cannot pop like this. So anyway, but this is bad idea to just copy and paste and change push to pop. You really have to reverse the order. So I'm just going to get rid of this and get rid of this. And let's take a look at the notes regarding the ESP register, which we mentioned already multiple times. So ESP register serves as an indirect memory operand, pointing to the top of the stack at any time. Like I told you, whatever is on the stack, right? So this is our stack right here, and we happen to have that ESP is pointing to some place here. So this is the last value that was pushed on the stack, and it's available through ESP. You can use ESP as indirect memory operand, which means just basically using the square brackets to go to memory in the stack and get to whatever was pushed on the stack last. As program adds data to the stack grows downward from high memory to low memory. We already spoke about this. When items are removed from the stack, the opposite thing is happening. When we push word values, the ESP is manipulated by 2 because word is 2 bytes in size. And when we manipulate double words, like we did over here, push double word size register, push D, which means push double word 5. These are all double words. So ESP is subtracted and added 4, because each one of these values on the stack is exactly 4 byte size. Like I told you, avoid any kind of word manipulation in x86 mode. If you're in real mode, in real 16-bit mode, then it's a different story. But in x86 flat memory model, I should say, right, the flat memory model, 32-bit, that all information is placed in one huge 4 gigabyte size memory segment. You just you should only be using 32-bit values when you're manipulating your stack. All right, so let's just assume that in our example right here, register changes in multiples of 2 or 4, but let's just assume the 4. And there are instruction push word and push double word, which we use here with an immediate value because we need to specify it. You cannot just do it like this, okay? So that would be incorrect. Okay, so we use special instruction push D specifying double word. Now, none of the push or pop instructions affect any flag bits, so the flags are not affected at all. And you cannot push byte size registers. So push AL simply is going to give us an error that this is bad instruction operand. You have to push the entire EAX if you really are thinking of preserving AL and with all with all conclusions from there. So just remember that byte size elements cannot be pushed on the stack. Now the flags or E flags can be saved by instruction push. Let me see. There's instruction push FD. So push FD will it has no operand, so this will preserve E flags. Okay, so if you want to preserve your E flags on the stack, you can do that, and the corresponding instruction to restore, right? If you want to restore E flags is pop FD, right? So basically meaning is pop flags double word, which is the entire E flags register. And again, notice that the sequence of these Push instructions is exactly the opposite order of my pop instructions, because that's the order in which we're supposed to train ourselves to work with the stack, basically the reverse order of pop sequence. And so more example, like right here, we're trying to use an example of pushing first the word and then double word. Okay, so apparently, again, just to explain because we're using this EAX example right here, so this is a good place to take a look at the memory. So right before, we're just assuming that this was the last thing placed on the stack. So therefore, ESP register, if I can use this right here, the original ESP register, before push EAX, is pointing to the top of the stack, which is this, right? So suppose that this is the last thing that was saved right here, and this is where we're pointing to. Now we're going to say push, right? Push EAX. And EAX contains 12, 34, 56, 78 bit pattern. So these are the hexadecimal numbers. So what happens is that the stack pointer is adjusted towards lower memory addresses. So the new position of the stack is right here, as shown in this picture. And so now we have the space, and this is how everything is written. So basically, the lowest byte is written into the lowest memory address, which is right at the very top of this ESP right here, right? And the highest byte is written into the highest or higher portion of memory available with this 4-byte memory that was used to save register EAX on the stack. And of course, everything is happening in the reverse order when we pop. So when we say pop EAX, what happens is that first we get the value from the stack. So this entire thing right here is loaded into register EAX, and then register ESP is adjusted to point to the next or the new top of the stack. So this is going away, right? So this is no longer used. This is an example of this use of stack as temporary memory area, right? So the last thing that we were discussing here was pop EAX, which is instruction right here.